Okay, everybody. So what we are doing now is part 2 of the practice midterm 2 solutions. All right, let's scroll down to where we left off. Problems 1 through 5 are done in the first video. Problems 6 through 9 or 10, whatever we have, will be done in this video. All right, let's get going. So problem 6. So find the equation of the tangent plane to a surface. Okay, at the point where x equals 0 and y equals 1. So let's see here. Let me think about this for a second. There might be 2 points. Let's figure it out. So if we go and we put in the x equals 0 and y equals 1 into this equation, we could find the z value. You might not have realized it was missing, but it is, right? So in order to find the equation of a plane, we need a point and we need a direction, a normal to the plane, right? So the deal is that you've got like generic 3D graph here. Let's say generic surface. And then somewhere on this surface is a point. And that point has a normal to that point, and that's the plane that we need to calculate. Okay, so we need the point and we need the direction vector for the normal to the plane, which will come from the partial derivatives. So the point that we have so far is x equals 0, y equals 1, and then there should be a z value, but they didn't tell us the z value. Okay, so kind of off to the side maybe. Well, no, we'll just do it right here. I'll try to calculate that. No, I'll do it here. I changed my mind. So the equation of the surface is z squared equals x squared e to the y plus sine x. And we know that x equals 0 and y equals 1 at the point we care about. So fill those in. So x equals 0, so we have 0 e to the y, but y is 1, so 1, plus sine x, but x is 0, so we have 0 plus 0, so we have z squared equals 0 or z equals 0. So this was the missing point, or the missing coordinate of the point that we needed. So the point is actually 0, 1, 0. So this is the point that we need, right? And we had to calculate that ourselves. Now, the other thing we need is a direction vector, a normal to the surface. So we'll call it n, and what it will be is basically it will be the gradient evaluated at the point that we care about. Okay, or you can say it's going to be fx, fy, fz at the point we care about, which is 0, 1, 0. Okay, so in order to do this, we need to calculate fx, fy, and fz, right? So that's what we'll do. So in order for this formula to be correct, you need to move this to the other side of the equation, because this is only the correct formula for the normal to a surface if your surface is set up as f of x, y, z equals a constant. Okay, so ours is not quite written that way with the z squared on the left. So we will take this, z squared equals x squared e to the y plus sine x. We can move everything to the left or everything to the right. It doesn't matter. So I'll move the z squared over to the right because that's the easiest. X squared e to the y plus sine x. minus z squared. Okay, so this is the f of x, y, z. So then we need the partial derivatives. So fx is going to be the derivative with respect to x. So partial of x squared e to the y with respect to x is 2x e to the y. Partial of sine x with respect to x is cosine x. And then this has no x's, so this is it for fx. We need fy. So derivative of e to the y is e to the y, so we have x squared e to the y, and there are no more y's. So this is done. Then we've got fz. Z is only here. The partial with respect to z is going to be negative 2z. Okay, so I have my partials. So we evaluate them at the point that we care about. So evaluate at 0, 1, 0, right? That's the point that we care about. So we have fx 0, 1, 1, 0 is, fill it in. We've got 2 times 0 e to the 1 plus cosine 0. So what do we have there? Let me actually just write this over here on the right. So that's just going to be 0 plus 1, right? So it's 1. Then we need fy. Fy of 0, 1, 0. So we have 0 squared e to the 1, which is 0. Then we have fz at 0, 1, 0, which is negative 2 times 0, which is 0. So overall, what do we get? Well, we're going to have a normal vector here of 1, 0, 0. So at this point, we've got the two things that we need. We have a point and we've got a normal vector. And if we have a point and we have a normal vector, then we can write the equation of the plane. So how do you do that? Well, there's two different ways to go about writing the normal or writing the equation of a plane. The way that I am going to do it is I'm going to start with this form, ax plus by, ax plus by plus cz equals 0. Nope, equals d. So that's the equation of a plane. The ABC is your normal vector. So we have 1x plus 0y plus 0z equals d. So we just have x equals d, very simple plane. And then in order to calculate this d, which is a constant that we need to find, we're going to plug in the point, which is 0, 1, 0, and then we will find the d. So or we'll say plug in 0, 1, 0 to find d. So of course, it's just x equals d, so we're just going to have 0 equals d when we plug that in. All right, so what does that mean? That means that our plane should simply be this formula with the d equals 0 plugged in. So our plane is simply plane. Looks like it's just x equals 0. Now let's see if that makes sense. Hopefully it does, but we will look. Trying to think if this will work okay. GeoGebra, start calculator, 3D calculator. What's the equation of my surface It is somewhere z squared equals x squared e to the y. You know what? Wait, we can hold on. We can see these both at the same time. Maybe. Oop, maybe. Okay. So what do we have? We have z squared. Oops. Z squared equals x squared e to the y. I'm going to need a function. E to the y plus sine x. Go. It didn't plot it? Okay, well that's did you plot it? Hmm. Not really seeing a surface here though. Maybe I can do this. Well, it's a little bit disappointing. We can try to plot it on Wolfram Alpha. No guarantees that this will work either, but we can try it. What I was hoping to do was to not have to. Oh, you know what? Wait, I have an idea. I wonder if I put the z. This is my last try, by the way. So if I put like a z here, okay. So this is z. So if I go z equals, and then we can't see it, but if I go square root the z's. All right, hold on. I guess I have to type the whole thing in again. Sorry, just iPad stuff. Lovely. Um, x squared e to the y plus sine. Uh-oh, it's happening again. X. Okay, there we go. Um, Now technically, this is only half of the surface. So I wonder if I can duplicate this. Duplicate it. And then if I go to the beginning here, and if I go z equals, and I put a minus, boom. This is apparently the surface that we're trying to find the tangent plane for. So if you look at the point that we're looking for, the point was 0, 1, 0. And I think you might be able to tell, well, I can just put it here, parentheses 0, comma 1, comma 0, enter. I can't really zoom in there, but can you see it? The point A, it's a bad color. Can I change the color? Hold on. I can't change the color easily. Okay. But you see it there, right? Kind of, maybe. Can you see it there in the background? So that's the point that we're looking at. And then you might even be able to see that the tangent plane there should be vertical. And so if I plot the plane, just x equals 0, you'll see you get a vertical plane. It does go through that point that you can't really see in the background. Um, and it is tangent to the surface. So this all actually worked out, even though the equations are very simple. Um, this does appear to be the correct tangent plane. Of course, you didn't need to graph it, you just needed to come up with it. So Took a while to do that, but I think it was worth it. We saw the picture. Okay, next question. So this is chain rule. Okay, so um, basically, if you look here, we have V has R's and H's, but then R has T's and S's, and H also has T's and S's. So um, it'll be important when we get down to the next step. But just a summary of what we have there is you have a function called V, and V has an R and it has an S. No, it has an R and an H, sorry. And then if you look at the two highlighted green there, R has a T and an S in its formulas, and H has a T and an S as well. And we'll use this little picture I made in a minute. But the first thing it says to find is partial of V with respect to R and partial of V with respect to H. So we're just going to be looking at this piece for right now. So partial of V with respect to R is, I'll write it, partial with respect to R of, let me just rearrange this a little bit. How about pi over 3 R squared H, right? I'm just taking the over 3 over to the left. So this is what we're taking the derivative of with respect to R. So there's the R squared will just go to 2R when we take the derivative, and we'll have 2 pi over 3 RH. That's it. Then we want the partial of V with respect to H, which is the partial with respect to H of pi over 3 R squared H. Partial with respect to H of H is 1, so we'll have pi over 3 R squared. So that's done. So that's all we're doing there, is taking those derivatives. Then we need to find the partial of R with respect to T and the partial of H with respect to T. So we need these formulas. So let me write them. R is T squared plus S, and H is ST. So partial of R with respect to T is, I'll write it, partial with respect to T of T squared plus S. So partial with respect to T of T squared plus S is 2T. Then we have partial of H with respect to T, which is partial with respect to T of ST. And partial of T with respect to T is 1, so this will just be S. Okay. Now it says use the chain rule to find dv dt, or partial of V with respect to T. So let me take this, move it down here. We'll try to get that again. Try that again. Move it. Why you are doing this to me? Okay. So this little tree thing where V was a function of R and H, R is a function of T and S, H is a function of T and S, that actually tells us the chain rule here. Basically, when you have a line from any variable to any variable, you can think of there as being a partial derivative there, or that's what we're going to use this chart for. So like between the V and the R, you could write dV dr, for example. And between the V and the H, you could write dV dH. And then between the R and the T, you could write dr dt. And between the R and the S, you could write dr ds. Same thing over here, dH dt and dH ds, right? And then the idea is if you want partial of V with respect to T, then you start at the top where the V is, and you take every path that takes you to a T. So you go from the V to the R, Whoa, how'd that happen? V to the R, and then from the R to the T. And then also you have to go from the V to the H, and then from the H to the T. So those are the two ways to start at V and end up at a T, right? Because we have a V and a T. That's why we're picking them. Okay. Now, what you do is whichever branch you took had a partial derivative associated with it, you multiply them. So when you go from V to R and then from R to T, what you want is this, this one and this one, right? When you go from here to here to here. This one we don't want because this one is for S and we're not doing S. Okay, same thing over here. We don't want this one that has an S. Just this one and this one. So when you go from, we get a different color. When you go from V to R, that's a dV/dr. dV/dr. And then when you go from R to T, that's a dr/dt. So you go dr/dt plus, and then you take the other branch, which is dV/dh, dV/dh, and dH/dt, dH/dt. Okay, and so this is the correct chain rule for this problem. All right, so then what do we have to do? Well, we fill in what we have for numbers and so on. So what's dV/dr? We calculated that up top, right? dV/dr is right here. Actually, let's just take that. Not take it, let's duplicate it. Why is it doing that to me today? Not letting me, it doesn't want me to scroll with it. So that's dV/dr. And then you need dr/dt, which we also have. It's right here. I'll just write it, 2d. And then we have dV/dh, which is up here. So there's the dV/dh, and then you have dH/dt, which I can see is just S. So this is what we get. So dV/dt is 4 pi over 3, and then we have an R, an H, and a T. And I'm going to come back to this in a second. And over here we have a pi over 3 R squared S. And technically this is correct, but the bottom level here has S's and T's, right? And this has R and H and S and T. It has all the variables in it. We usually don't want that. If your bottom level here is T's and S's, then we should want everything to be T's and S's. That means we don't want an R, we don't want an H, and we don't want that R. And the way we're going to get rid of them is we have formulas for what R and H are, right? We have, where are they? Where's R and where's H? Here they are, right? R is T squared plus S, and H is ST. So these two things here, we can take those and we can plug them in to our formula, and then everything will be in terms of T's and S's with no R's or H's. So we have 4/3 pi, and then an R, but R is T squared plus S. Then we have H, but H is ST. And then we have T, which is T. And then over here we have pi over 3 R squared. R is T squared plus S. So T squared plus S squared, and then S, which is already an S. So there we go. And you could multiply some stuff out here if you want, but I won't. Just going to leave it like this. Okay, so that's actually pretty easy. The chain rule is not that bad. You just have to draw out that little tree, um, and then you can write out what the chain rule says. All right, next question. What is this? Differential. Okay, so should be pretty straightforward. Uh, find the value of z at x, y equals 3, 0. Sure, that doesn't seem hard, right? Z equals square root. We put in a 3 for x. We put in a 0 for y, and we have z equals, what do we have? 3 plus, well, it's just going to be 1. So we have z equals 2. All right, done. Find the first partial derivatives of z evaluated at 3, 0. So we need the partial derivatives of z. So z is square root 3 plus, nope, not 3 plus, anything, x plus e to the 4y. X plus e to the 4y. So our first derivatives will be d, whoa, that's weird, dz, dx. So, the partial, formula from calculus 1 ddx of square root x is 1 over 2 square root x. You could do it with the power rule, but this is generally faster. So I just jump to there. So that's the derivative with respect to x, but you have to multiply by the derivative of what's inside with respect to x, and the derivative of what's inside with respect to x is 1. Okay. While we're at it, let's just do the partial with respect to y as well. So we'll start out the same way. And then you multiply by the derivative of what's inside with respect to y. So the derivative of e to the 4y is 4e to the 4y. 4e to the 4y. Y. Okay. But we were supposed to evaluate these at 3, 0. So dz dx evaluated at 3, 0 is, well, let's put it in. So we have dz dx 1 over 2 square root 3 plus e to the 0 again. So of course this is 4. Square root of 4 is 2. 1 over 2 times 2. 4. And we want partial of z with respect to y evaluated at 3, 0. So that will be on the bottom. The bottom's still the same, right? So I'm just going to kind of cheat here. No, I won't. I'll write it 2, 3 plus e to the 0. On top, we have this thing. So we have 4e to the 4 times 0. So what do we get? Well, on the bottom, right, this is 4. Square root 4 is 2. 2 times 2 is 4. So 4. And then e to the 0 is 1. So 4. 4 over 4 is 1. Okay, so we have our first partial derivatives there. Okay, so then they say find the differential of z dz. So in case we don't remember that, let us go find calculus volume 3. Differential should be in the section on partial derivatives. 4.3. Tangent planed, actually, probably. 4.4. And basically, the dz is going to be part of the equation of the tangent plane. I'm looking for the actual thing I want to find it. There you go. There you go. So you see the total differential there. dz is fx, so partial of f with respect to x, and then a dx at the end, and then partial y with a dy on the end. So basically, what we just saw was this formula. dz is fx at the point. I'm just going to write p for point, just to be lazy. dx plus fy, I'll say again p for the point to be lazy, dy. And we've just calculated those, right? This is this, and this is this. So you just write dz is simply 1/4 dx plus 1 dy. And that's your differential. Okay, now what is the point of that? Well, we can use it to approximate things. So what you can do is you could say that this is a dz, like these are differentials, but you can think of it as being like a delta z, where that's like change in z is approximately equal to 1/4 times the change in x plus the change in y, where that's change in z and change in x and change in y. Okay, so the idea is basically the z value evaluated at this point, 3.1 comma looks like negative 0.2, it's not equal to, well, I shouldn't say it's not equal to something. It's approximately equal to the z value at 3,0, right? Because this point here, this point, 3.1 negative 0.2 is close to 3,0. And 3,0 was where we've been calculating all these things. Okay, so z evaluated at this point is approximately equal to z evaluated where we did everything, plus this delta z, which we also need to evaluate at that 3,0. No, that's not quite true. It's plus the delta z, but you need to figure out the change in the z in order to do this. So let me just start filling in numbers here. So what is z evaluated at 3,0? I think we started with that. It is 2. Okay, so that's where we're starting at. And then you want plus this 1/4 delta x plus 1 delta y. And what those are the change in the y from this point, from the 3,0. So if you go from 3, if you go from 3 to 3.1, then the x went up by 0.1. So the delta x is 0.1. Okay, and if the if the y value goes from 0 to negative 0.2, then the delta y is negative 0.2. So that's your delta y. And so from the 2 that we started with, this is how much the function value should change. So you just punch that into a calculator, or not really, actually, I guess, and you get what you get. So this is 2 plus half of 0.1 is 0.05 plus negative 0.2. So you work that out, and it'll be something. I don't know why I'm using a calculator, except that my brain doesn't work right now for some reason. 2 plus 0.05 minus 0.2, and we get 1.85. And that's what we're doing. Okay, could have written that last part a little bit nicer, but you can look at the sample problems in that section if you want to see a little bit nicer way to do it. Okay. Next question. All right, so we have a function. We want the gradient. Of course, the gradient of f is by definition here. You put fx in the first spot, you put fy in the second spot. So we just need those partial derivatives. So the partial of this function with respect to x, we need the product rule, right? Because there's x's here and x's here. So we use the product rule there. Partial of x squared is 2x sine xy cubed plus, then you want x squared times the derivative of the sine part. Derivative of sine xy cubed is cosine xy cubed, but then you have to multiply by the derivative of what's inside with respect to x. So the derivative of what's inside with respect to x is y cubed, right? Comma. Now we need the partial with respect to y. There's only one y, right? This is the only y in there. So the partial is going to be x squared, and then the derivative of sine is going to be cosine xy cubed times the derivative of what's inside with respect to y. The derivative of y cubed is 3y squared, and then x. So we have 3y squared x. Okay, there we go. So there's our gradient. There's not a lot we can do or would want to do to try to clean this up. I'll just put everything in front here. So like on the second one, we have a 3x cubed y squared cosine xy cubed. Okay, so there's your gradient. Now it says at this point pi 1, in which direction does f decrease the fastest? Well, the point is that if you are on a surface, so again, I'll draw my generic looking surface here. When you're at a particular point, the direction where the slope is the steepest, hey, how'd that happen? The direction where the slope is the steepest uphill, that's the gradient of f. So gradient f points in direction of greatest increase. We want decrease. So what's that mean? It means the opposite direction. So if gradient f is where it increases the most, then negative gradient f is the direction where the slope is the steepest in the other direction. I kind of, those gradient vectors aren't drawn correctly. Oops. But because, stop it. The reason they're not correct is because what's actually true is like they are two-dimensional vectors here. So like it's hard to say, like if you had a point like x, y, like on the ground, then the gradient of f points that direction, because if you were here, that's the direction you go to go up. But it's still, this is a two-dimensional thing, right? So it like exists in the plane on the ground. I drew it pointing up. That's not what it does. Okay, so gradient f points in direction of greatest increase. We want negative gradient f because we want greatest decrease. Okay, so what are we going to do? We just need to plug in pi comma 1 into that formula that we just had there. Also put a negative on the outside. So we just plug in the numbers. So we have 2 pi sine pi times 1 plus pi squared 1 cosine pi 3 pi cubed. I feel like I made a mistake here. Let me just look at this real quick. When we took the derivative with respect to y cubed, we had 3y squared x. So, okay. I feel like I'm making a mistake here. Like maybe this was supposed to be a, I don't know. Okay. Anyway, let's keep going. So sine of pi is 0. So like this entire term drops off. Then cosine of pi is -1. So this is negative pi squared here. That. And then on the other side, again, cosine pi is going to be -1 and 3 pi cubed. So I think I have -3 pi cubed. I'm going to check on something real quick. These are my notes from earlier doing office hours. See, I wrote this, pi squared, 3 pi squared, and that's because when I did the derivative, I wrote, right here. When I took the derivative of this, right, dy of xy cubed, it's 3y squared, but it's x times 3y squared. So I just missed an x there. So that should have had an x when I did that earlier. So that should have had an x, which is an extra pi. So that should have been a 3. Okay. Right, so that looks right, I think. So we have negative this, and they are both negative, so negatives will make them positive. So pi squared, 3 pi cubed. Okay. And that's going to be the direction, right? That's a direction. And that should be the direction where f decreases the fastest because we stuck the negative in front of the gradient. All right, then we want the directional derivative. So how do you do a directional derivative? Well, you do a dot product between the gradient and a unit vector in the direction that you want. I don't know why I'm scrolling to it here, but I am. Give me a formula. There we go. So if you read this, it says exactly what I said. So notice that it says in the equations, you can't really see where I'm pointing, but it says gradient f dot with u, and it says u is a unit vector. So the directional derivative of f in the direction of u is given by the dot product of the gradient with the unit vector. Okay, so dot product that. Okay, so how do we do this? So what we need is, first of all, we're given this direction, but that's a vector, let's say 2, -1, that's not a unit vector. So to make it a unit vector, we have to do that vector over its magnitude, right? So it's 2, -1 over the magnitude of that vector, which is 2 squared plus 1 squared. So we end up with, that looks like a square root 5 on the bottom. So we end up with 2 over square root 5, -1 over square root 5. So that's my u. So then my gradient, or sorry, not my gradient, but my directional derivative. So look at the notation here. Directional derivative in the direction of u of f at a point. So directional derivative of u of f evaluated at pi comma 1 would be the gradient of f, evaluated at pi comma 1 dot with that u. Now we've calculated these though, because the gradient of f evaluated at pi comma 1, we actually did that, well actually technically we didn't. You have to be careful here. So notice that what we did, I asked you what point does f decrease the fastest, and it was this one, right? But this is the gradient, and we had an extra minus on the outside. So the gradient actually has negatives here. Negative pi squared, negative 3 pi cubed, and then dot product with 2 over root 5, negative 1 over root 5, and this is a dot product, so we actually have to do that dot product. So we multiply this by this. We're going to get negative 2 pi squared over root 5 plus, and actually it will be a plus, these two multiplied together, right, negative and a negative will be a positive, so we're going to have 3 pi cubed on top over root 5 on the bottom. Looks right. So this must be du of f in the direction pi 1. Just to say it again, the reason these have negatives on here was because the gradient was the direction of fastest increase. In the previous part, I asked for greatest decrease, which was the negative gradient. And I kept that negative on the outside until this point. So the negative here is not part of the gradient. So this is the negative and this is the gradient. So this is the gradient. Not this. This is the negative gradient. Okay. So we did that. So there's our directional derivative. What it means is that's the slope in the direction. And, oh, that's it. I thought we had one more question. We do not. 5, 6, 7, 8, 6, 7, 8, 9, 4. Okay. So there were only 4 questions to do, and we did them. Great. So, yeah, that's it. Test should be up late Thursday. It already is late Thursday. It's 11 p.m. Or tomorrow morning-ish. See what I can do. All right, that's it for now.